Well, as I live and breathe, folks, and most of us still are, thank God. And on the screen, at least most of us are here. We've reached another milestone, folks. Welcome aboard the beginning of our big 60 year right here on Zoom and on our YouTube channel of the SBAU Astro Hour. It's our 260-second program for a special once a week vlog podcast for the Santa Barbara Astronomical Unit, the longtime astrophysics and telescope club based right here in Santa Barbara, California, at the Museum of Natural History. My name is Ronnie Heron. I'll introduce you in a minute to my cosmic comrades on screen. And we just love this science and invite you to submit your questions or comments at the bottom. Travel along with us, as well as check our club out at sbau.org. We are looking forward to our big March 6th general meeting this Friday night in the museum's Fleischman Auditorium with Dr. Rosalie Lopez, JPL, speaking on volcanism in our solar system. Star Party will be another week after that on the 14th at night. Meantime, here's what we're talking about. I'm going to take a look at some rare types of stars called Wolf-Rayet. For example, WR122, we call the nasty one, with some riveting web pictures. We got a blood moon developing early tomorrow and throw in a full lunar eclipse overnight. There's a one-time only comet. Get this, it's passing us by. It's called C/2024 E1, the Virtuos, and it's apparently leaving us, leaving our solar system for good. Inside the Sculptor constellation, NGC 300 is the Sculptor Pinwheel Galaxy, also called the Caldwell 70. And we're going to take a look at a great variable star called Mira. What exactly are Milankovitch cycles? We're going to take a look at it. It has something to do with ice. And just for the record books, I'm going to add this. It's from New York Times last Wednesday, the 25th. 70,000 antennas are on a new radar system being installed in Norway that's going to kick off operation this summer, that's going to be used to study the aurora borealis and space weather. My name is Ronnie. I'm vice president. Let's meet the president, the man in charge here of the Astro Hour, Mr. Jerry Wilson, our beloved president. Good morning,
Good
sir.
morning, everybody. Good morning, Joyce, and good morning to my grandkids, Calvin and Riley.
Okay, and I hope they're all watching. They can watch it if they don't see it live. We're archived. Here is our co-pilot and our fact checker, outreach coordinator Chuck McPartland. In front
Howdy,
of
howdy.
he is also married to a Pat. Jerry's married to Pat Forgy, and Pat McPartland is your wife, selling off all the merchandise and also running the Treasury Department. We're missing a fifth guy, but Tom Whittemore joined us.
Morning.
Corbett Westmont. Hi, Tom.
Morning.
Baking his way into oblivion these days, but man, he misses those years in the lab. Couldn't put one sourdough pile of dough in anything, could you there? But yeah,
No, but I brought it for the students often.
that's true. And you had a
Fresh
lot of,
bread, fresh
yeah,
bread.
and you had a pretty damn good newsletter, and you have for a
Oh,
long
thank
time.
you. Yeah, the idea
Okay.
was to honor art, so I put two photos in, one with a little funny thing on it, but the other one pretty, serious. He's
And then
he's he's a great man. He's a
you have a
great
life
man.
with a pair of binoculars as a bird watcher, an Audubon Society member, right? As
Right,
well.
right.
Well, bless your heart. Wonder who took over or who the new president of the Theater Organ Society is now that we lost Bruce back in December. He was the president. Anyway, we're missing our fifth guy, but he'll join us any minute now, I hope. Tim Crawford, who's married to Karen. Tom is married to Maureen, and he edits our newsletter. And we start every show as we are this new year, the sixth year. We started March 1st, 2021, as we're coming out of the pandemic.
Wow.
Here are the sillies, the president's forwarded tunes that are going to have to be enlarged. And okay, that one is, oh, what did I look? What did I write down? What's over here? Yeah, Jerry, you want to lead it? That looks like a superhero talking to a lab scientist about something.
I just bought a book about lunar activity and space traveling. It's fascinating. I can't wait to see how it ends. That's great, Brewster. Glad you're taking an interest in science. So it says, good night, moon. Good night, jumping
That's
over the moon.
that's a great book.
Yeah.
Green cheese for everybody.
Yeah.
Okay, and here's the couple. Chuck, why don't you read that to us? What's she saying to him as they watch a very dark moon?
Yeah, well, they're looking up at the moon and it's got a kind of mottled appearance. And they're saying, sending all of our trash to the moon did solve a lot of problems, but it sure is a bummer to look at.
Pretty good.
Called the new Tahigas landfill moon.
Yeah.
Okay, Jerry, she's doing her spring cleaning and a big surprise, and I know this has happened to every one of you by your lovely wives.
No, they've learned, they know not to touch this.
Do they really?
Yeah.
Well, let
She
me
says, surprise, now that it's getting warmer out, I thought I could help out and give that dusty old telescope of yours a good spring cleaning. Oh, yes, I also put all your eyepieces in boiling hot soapy water to soak. You can thank me later, honey.
Oh, yeah.
And she also uses Comet Cleanser because it has a spacey name.
Yeah.
What it doesn't show is that she happily installed a new bright light in the backyard, honey, so we can see better.
Now this, yeah. Now this telescope is what we call a Dobsonian mount, and it's a Newtonian telescope on a Dobsonian mount. It's the most common form of, I guess, say, large telescopes for visual use.
Doesn't have the tube in the middle.
No tube.
No.
I added two last night. This is one of them.
Oh.
According to
guys
our
saying-
analysis, those are the remains of a film shoot in a galaxy far, far away.
Oh, I see.
We're
Coming our way,
referring to the
yeah.
Star Wars film.
Okay. Here's another new one. I don't recall this
Yeah,
one.
this is the Flat Earth Society has won a free trip to space to prove it. So cheer up, gang. Even though it appears we were wrong, at least we won this free space flight tour. Okay, mission control, we get it. You can fly us down now. Mission control.
You ain't coming back, guys.
Yeah.
Okay, looks like we're on an icy moon orbiting Saturn, but what's the story here?
The kids couldn't bear seeing him without a helmet.
So
Yeah.
they put a helmet on the snowman. A spaceman snowman. Okay, got it. Okay, the talking sticks.
Astronomers asking researchers from different departments to help them identify the little red dots in JWST images. We covered this about 3 or 4 weeks ago.
Right.
Entomologists, how they view it. Oh, those are clover mites. Computer scientists, oh, a stuck pixel.
The pixel.
Dermatologists, cherry angiomas. Graphic designers, no, those are vermilion or maybe jasper. Can I see your color settings?
Well,
I'm
I
glad
hope I
you
don't have
handled
to-
that one, Jerry. I couldn't pronounce any of them.
Okay, might as well introduce Tim Crawford, who's married to Karen, and Tim is on board. And
Hi,
nice
Tim.
of you to join
Hi,
us.
guys. Hi, Ronnie.
Here's a photograph of me as at a younger age, when I was much younger. How about you guiding us through this, Tom Whittemore?
It says, so what happens if we're not the first one to reach the egg? We're tadpoles, Ted. Stop looking up stuff on the internet.
That's good. I like that.
They do look like that, don't they?
Yep, misinformation.
Yeah.
Well, far out. Those are funny. That gets us in a good mood to talk about serious stuff in space now. Now that we're complete livesome.
So Ron, you should check out Tim's t-shirt. There's a story behind this.
Well, stand up, Tim, so we can see it.
Oh, this is the guitar one, though.
Oh, okay, okay.
It's not the other
Okay.
one. Yeah.
Okay.
We're going to talk
Oh,
briefly
boy.
about Wolf Rayet stars, which I always think in my mind of Wolf Riot, but these are a very, very big star, and it's a short phase at the end of their life.
Yeah.
And what has happened is that the star is very big, and because it's big, it's very hot, and so it has a tremendous solar wind or stellar wind blowing off, and it manages to blow off its outer layer of mostly hydrogen. So when you turn a spectroscope on the thing, you see other heavier elements that would normally be hidden under the hydrogen layer in most stars. But here you see the surface, the core, not core, but an inner layer. And they're dominated by nitrogen type, carbon type, or oxygen type spectra. So they are the brightest stars in the universe, though they're very rare and only a few hundred are known in the Milky Way.
They're hot blue ones. They're big blue or they red giants?
They're
Let's
hot,
see.
Ron, so they're not red.
Yeah, they're very hot. They're blue and white O-type stars.
Yeah, very
Jerry, which type is the crescent?
That's a
Which
wolf
one?
ray.
yeah.
But of the carbon type or oxygen, is it the oxygen type?
Oh, I don't know.
Yeah.
So Betelgeuse is a giant, but it's not that hot. Not as
No.
hot as the blue one.
It's a super giant.
Well, I know that. I know how big it is. I just
Okay,
red.
The term for it is not giant. It's a super giant.
Oh,
so Wolf-Rayet stars also produce a Wolf-Rayet nebula, which are surrounding shells of ejected gas.
Mm-hmm.
And let's see. Oh, I didn't list nasty in there. But anyway, this is the Hertzsprung-Russell diagram. And this over here is luminosity. It's how bright they are. And these WR, that's Wolf-Rayet stars. And these are these things here that go up to 20 solar masses, 30, 40, 60, and 100.
Yeah.
These are really big things.
Tim,
Christmas back there.
I peeked ahead, and it's a WN. It's the nitrogen type for the Crescent Nebula.
Oh, thank you, Chuck.
Okay. Yeah, that's in a caption, I think.
Yeah.
Okay. Now this one is oh, I can't read the caption, but this one is a picture of the Wolf-Rayet star NAST1, nicknamed Nasty One, and it's got a trail from the bright star, and it goes around to a white dwarf that is accumulating this crap, and it's also. Not all of it is landing on the white dwarf. A lot of it is going around in this nebula, and that produces that.
Oh,
So this is a candidate for a type 1A supernova when the white dwarf collects enough hydrogen, because it's primarily hydrogen that comes off.
but the brighter one on the right is the Rayet, the Wolf-Rayet.
Yes.
Yeah.
Okay, got it.
Now that was an artist rendition, as I recall.
Yeah.
And this is an actual photograph of it's a binary star, and this is a clump of that material. This is an outer arm or ring. So this is the data that previous one, artist impression, was made from. And it's NAST1 or Nasty One. And this is a Hubble Space Telescope picture. So this is 2 seconds of an arc across. And that is about 3 seconds of an arc across, roughly, is the size of stars when I take pictures of the sky from my backyard, produced by atmospheric turbulence. So 3 second star diameter, about like this, would be a good picture for me. Good tracking, good air. This is obviously no air.
Wow.
This is another example of a Wolf-Rayet that has thrown off its outer layers. They produce these nebula before they go through any other stage of their life, such as an explosive output. And it was interesting because these are really like planetary nebulas, which happen from more of a sun-like star.
Wow.
But the mechanism is different, similar but different. So one that I've taken a pic. This is one. What is this? The Dolphin Head Nebula.
Yeah.
Yeah, and that's the envelope from a Wolf-Rayet star.
looks like a teddy bear nebula.
Is that the teddy bear?
Yeah.
I think this one's called the porpoise head or something like
Porpoise
that.
head. Yeah, that's what I remember it as.
Oh, okay, I got you.
Yeah.
And where's the Wolf-Rayet?
Right
Right
there.
there, in the middle.
Now this could be one of my photographs. This is the Crescent Nebula. There's the Wolf-Rayet star. And this is the nebula that's thrown out. It's also got a lot of other, if you do a deeper exposure, you bring out all sorts of other nebula that's much fainter around here. But this is the primary Wolf-Rayet planetary nebula part.
It's also called Van Gogh's ear.
Oh, I never heard that.
Yeah, yeah. Van Gogh's ear. Gary, this is the one that I was up at Lake San Antonio, and Steve Kennedy had me walk up this ladder or climb up the ladder to a 24-inch mirror, I think it was. And he had a tracking platform, and he dialed it in. And he says, "Go take a look and tell me if it's there." Dead center, and it looked like that. It was unbelievable.
Could you see the nebula?
Yeah, oh yeah.
Okay.
It just incredible. It wasn't red, but it was,
Yeah, our eye doesn't see color at faint levels.
definitely Van Gogh's ear.
Yeah. Now this is a typical spectrum,
Spectrogram.
and this is one of the 3 original Wolf Riot stars identified. The horizontal axis is in wavelength in angstroms. So this over here is in the ultraviolet. Well, yeah, they got color down here so you can reference it. And so this is the sodium doublet in here. And these are out in the deep red around hydrogen alpha, which is probably this one. And you can see there's some hydrogen, but there's a lot of other stuff out here that is produced deeper in the star.
It's 65, 63, according to that.
Okay, so this one,
Yep.
this one is the hydrogen. Oh yeah, it says hydrogen alpha
Yep.
right there. And this is carbon.
Yeah, there's a bunch of carbon.
Mm-hmm.
So different elements up here on the color spectrum. Is that how that works?
Yeah.
It's a spectrum. Yeah, that's how you can tell what elements are there and what temperature they're at and how they're moving.
So most stars,
nitrogen.
if you looked at our sun, it would mostly be hydrogen. Most of the light would come from hydrogen. Here, hydrogen is a minority player. It's you're seeing farther down into the star. This is a carbon-rich Wolf Riot star.
Huh.
And those numbers at the bottom, Ronnie, those numbers at the bottom refer to nanometers.
No, they refer to
No.
angstroms.
Those got to be angstroms.
This is in
Angstroms?
nanometers, put a decimal point before the last 0.
Right, then you get nanometers.
Okay.
No, those are angstroms, Tim.
Oh, wow. Okay, very good.
Huh.
See, this is a carbon type star, spectrum dominated by ionized carbon and oxygen. We saw in that spectrum of the carbon, it was carbon rich, so it would be a WC star. And finally, the last one, I think this is WR31A surrounded by a blue bubble. Yeah, okay.
That's a really nice one.
Yeah, it's very nice.
I know the crescent is visible, but are all of these kind of visible because they're so bright?
They're bright.
To
Go
a
ahead.
backyard telescope.
They're bright because they're very luminous. Sirius is very bright because it's real close.
But
So,
I mean, for a backyard telescope, are they
I
mostly?
think some of these probably aren't,
yeah,
but
Okay.
some are.
yeah.
Yeah.
No, this looks exactly like a photograph I took in a 10-inch telescope.
Mm-hmm.
So I would say that you could see the central star visually, but not the nebula. We need one of your 24-inch to see the nebula.
Or Joe's scope.
Yeah,
Yeah.
It probably shows up in that.
Are we on to another topic, or could I ask one final question before you leave?
Go ahead.
What's the bottom line? Can you recap that diagram? Went by real fast. What makes them rare? Why are they big but rare?
Because when a star blows off its outer layers, it's running on, as it goes to heavier and heavier elements, it runs out of fuel faster and faster. And so by the time it blows off all of its hydrogen in the outer layer, because of a massive stellar wind, because it's so hot, it's getting up there where it's starting to make iron in its core, and that doesn't last very long. And besides this, the first one we looked at is dumping hydrogen, not into a space nebula only, but it's dumping it on a white dwarf star. So that white dwarf star is about to get angry and blow up.
Yeah, also, Ronnie, these stars are very, very massive. And when stars are produced, it's like a power law. If you're 10 times more massive, there are only 1/10 as many of you. And so they're
This,
rare just to begin with because they're very massive.
Yeah.
this
Oh.
sounds like a good candidate for a supernova, or
Yes,
Yeah.
they all end with a nova.
supernova.
When they hit iron, it's all over. And
Yeah, core collapse supernova. Or maybe even direct collapse on some of these that are big enough.
and yet Jerry said that little dinky companion, the white dwarf, might also go as a nova.
Supernova.
Both of them, the little one and the big one, could both be novas different times, or
Supernovas, yes.
the big one doesn't absorb the little one ever. It looked like it was right in the middle of it.
Well, it depends on how thick that stellar wind in the accretion disk is. If that's thick enough, that could slow down the orbit of the white dwarf by drag and cause it to spiral inward.
So if there's any exoplanets around that sucker with life, boy, they got to be pretty hardy life, I would imagine. To
Yeah, not
all that
very likely.
solar wind. Okay.
Any planets around those stars are polished bare.
Yeah.
I have a possible future talk or a talking point, Jerry. I understand there's some stars, so massive stars, they don't go to supernova, they go directly to a black hole.
Yeah, we just covered one, I think, last week or the week before.
Oh,
Yeah.
I see. I'm sorry, I missed it.
Yeah, we saw a star in Andromeda Galaxy that just winked out.
Oh,
Yeah.
you're right. I remember that.
Direct
Okay.
collapse, yeah.
Yep. I often miss things that are right in front of me.
Yeah, you're not the only one.
You're not the
Okay,
only
this-
one, believe me.
We're having an eclipse of the moon on tomorrow morning at 5:30 a.m. Central Standard Time, so you need to change it to what, 2 hours for us?
Yeah.
So this would be 3 o'clock, 3:30 a.m. Pacific Standard Time.
So the shadow of the Earth.
And that's the peak of the eclipse.
Yeah,
It starts like a half hour before that, as far as totality.
yeah.
Oh, interesting.
Wow.
Wow.
Now,
Hope I'll make
right
it,
along.
Chuck.
Their Bon Voyage comet.
Now this is Comet Wirshos.
You got to get Tom to pronounce this one.
I just say viejos.
Yeah, that. Okay.
Viejos.
Now it has multiple tails. It's a very interesting comet this way. This comet is believed to have originated from our Oort cloud, but it's on a hyperbolic trajectory from our Oort cloud. So it is leaving our solar system. We are the source of this. And it's those two other ones that recently went by that came in from deep space and passed through our solar system. This is one that's going to do that for other solar systems, but it came from our solar system.
Wow.
Did you get
What do
that?
you suppose? What kicked it out?
Proximity to one or more other stars that or other objects that gave it a gravitational boost. Just
Oh, the stars? Did you
no,
say
there's there's no stars in the Oort cloud.
That's what I said.
Maybe it started a long time ago when a star passed close to us. I don't know.
Oh, I see. Okay.
But this somehow has picked up enough speed to put it on a hyperbolic orbit, an open orbit. It ain't coming back to us.
Wow.
Something gave it a shove and it got out of equilibrium, and here we go.
Yeah.
And they know it couldn't be a giant elliptical that would take thousands of years. It's gone for good.
Right.
Wow.
Actually, it's just an alien spacecraft that said, "Oh, they're looking at us. Let's get out of here." That's where it's going.
And three tails? Why does it have three tails? What are the three? One of them is what? Solar wind?
Yeah, it's probably got cryovolcanoes on it like you're going to hear about on Friday.
Yeah.
Whoa. You're
Now,
kidding
this
me.
picture was taken several months ago, October or February 13, I think, 2026, about a month ago, half a month ago. And it's curious because this is a very nice image of NGC 300, which is a beautiful spiral. It's not up for us these nights. I couldn't get it to come up at night on my planetarium software.
That main tail looks like a twisted rope.
It does. It's got a lot of structure to it. Now
That's
this
because
is
we have an
one-
active sun.
Okay.
Okay. This is Weirshos. This is its trajectory through through Eridanus,
Mhm.
from Cetus, Eridanus, and up here into, what is that? Can't read it.
Looks like Taurus.
Okay, that's right.
What are
So
those?
anyway, it's going up here. These are dates. This is
Day
February
and hour?
28th, March 3rd. So it's right here today.
Hmm.
This is March 6th, March 9th, March 15th, 25th, and down to April 1st.
Wow.
What magnitude is this thing?
It's
I
like
think it's
12
about-
now, I think.
It's about 6, somewhere between 6 and 8,
Okay.
Ooh,
as I
They're cranking
recall.
up.
It's also leaving, so it's getting fainter.
Oh,
You
okay.
see that. This is I had to put this in here in honor of Chuck because he hates these.
Totally
Oh.
useless star map.
Yeah. So we are March 5th. We're not quite on this scale yet. So we're down in this area. So, and anyway,
It's another one that was good for the Southern Hemisphere.
yeah.
Yeah.
Uh,
Yeah,
they-
it looks more
they
like a
impose
check
lot.
word. Jerry,
So
looks
this is
more like
about
looks
go
more
ahead.
like a Czech word to me.
Czech.
A Czech, yeah, Czechoslovakian.
I didn't know there was much difference between Czech and Pole.
Yeah, I've I know Polish, but I know some Czech words. But see that S with the little diacritical, that accent, that shows up. That doesn't show up in Polish. That shows up more in Czech.
Okay.
Oh.
It makes the S sound like sh, like that. So I would say it's more like virchosh. That's how I pronounce that word. I bet you I bet she's a Czech.
In that region of Europe, all the W's and V's.
But Ron, you should check me on that.
Well, I just know that V's and W's are interchangeable, and I don't know why, of all the two letters.
Well, in Czech and in Polish, the W is pronounced like a V,
That's
like in
exactly
German,
what
like
it
in
says.
German, like in German.
And it's vice versa too, isn't it? Do they have a W sound?
Who does?
Germanic,
Oh
Polish,
yeah,
Czech?
like wir haben, we have WIR, wir. Jerry knows German, I think,
Yeah.
Gotcha.
and I know German.
Well, I just think it's amazing that our little solar system is throwing out our own Oumuamua. I wonder which star in the distance is going to be aimed at to go through someday.
Tommy,
Yeah.
it's a Polish astronomer,
Oh, it is. Okay.
Kasper Virkos.
Okay, Virchosh. Shosh.
Yeah,
Okay.
but you can't pronounce that one any easier than the other one.
Yeah. It must be Southern Poland then.
Yeah.
It was discovered in March 3rd, 2024.
Okay. Must be the Tatras. You must be from the Tatras.
Those of you that know German too, you know that they have Northern German, which they teach in schools, and especially in English schools, called Hochdeutsch or
Yeah.
High German. And then if you go down to the border near Switzerland and Bavaria, they speak a Southern accent German, and it's like slurred German, just like our Southern English is slurred. Sounds a little slurred if you were in regular English.
I had a friend who could speak Schwaben, from Swabia.
Yeah.
And I couldn't understand a darn thing. And
I can't pick up casual conversation in Bavaria.
Here's
And
something,
Switzerland
Tommy.
is
Guys,
we used to have a guy in our club. This was a running club up in Palo Alto, who was a Swiss German, and he spoke Schweizerdeutsch.
Yeah.
And it was hard to understand him too.
Yeah. It's very hard. They understand me perfectly, but they say things, then they laugh, and I didn't get it. So anyway, this
the
is
guy's
where
first name was Kasper, but it's K-A-C, Tom.
Yeah, Kash.
K-A-C.
Mhm.
Huh.
Yeah.
Okay, anyway.
this is where that comet is right now.
Okay.
And this is at 8 in the evening. This is in the southwest. So it's going
Oh.
down.
Mhm.
And unfortunately, 300 is not on this when that picture was taken, but it was somewhere down in this region.
Sculptor, yeah, that'd be way south.
Yeah. Now, this is the recorded magnitude of that comet as it came in and peaked. And right now, here
Oh,
it is in this. Let's see, this we're about here, about March 1st. So we're about here.
yeah,
And
it's getting dim.
what's that?
Getting dimmer.
Yeah, it's getting dimmer. So most things I read about it for this talking point was between 6 and 8. So it's probably lower than that now.
Wow.
So these scientists, they don't see the beginning or where it initially came from. We don't know whether it was Kuiper Belt or Oort cloud, right? Just
No,
outside.
when they find something, it's usually somewhere in this region, and then they go back to, because we take pictures of the sky all the time, and they go back to other plates and other pictures, and they locate that object, and so they can get this curve. It doesn't mean that they found it down here somewhere.
And to have this kind of velocity, it has to have come from farther out. More like Oort cloud than Kuiper belt.
Right.
Yeah, and you notice how all the data, Jerry, bundles up around 16th magnitude.
Yes, that's the
And
easy
that
one.
could be a fact of where it was in the sky too, right?
Yeah.
Yes.
They try to account for that, but
Mhm.
But the Kuiper is a belt like the asteroids, whereas the cloud, the Oort, is a giant bubble, right? Further
Yes.
out.
Right.
Both filled with the exact same thing, a bunch of
Yeah.
wet rocks.
Now this is NGC 300, which we saw in that other picture of
Oh, yeah.
the thing. It's a beautiful galaxy, and this is
it's really blown out in the center. I mean, it still looks good.
Yeah.
oh
It's
So,
really
Jerry, is
pretty.
this in the sculptor group this way? Is this
Yeah.
in the
it's right
sculptor?
next to the
Oh, it is.
sculpture.
Okay. Okay. Because was it 253 is down there somewhere too?
Yeah, silver coin.
Yeah.
Wow.
That's one of the most favorite you ever showed me, Tom. And that
Oh,
was
yeah.
great
That
team.
was San Antonio, Tim.
It was. It was at the
In the 18-inch I built. Yeah.
beautiful view, boy.
Yeah. Yeah. You could see the stippling in that darn thing, you know, from the clouds. It was really pretty.
Yep. We're talking about 253.
253. Yeah.
Coin.
Mhm.
Okay,
There we
this
go.
one, the center should be better. Yeah, it's beautiful.
That's
Beautiful.
gorgeous. Yeah.
Looks
I don't think
really
I've ever
pretty.
seen that one.
Got purple. Wow.
Yeah, this is a combination of different spectral regions, as I recall.
Mhm.
By bubble, wind impacting. No, oh, that's different. I'm reading the wrong caption.
It just says large set of different filters. So
Yeah.
Mhm. God, there's even a little galaxy way out in the distance there in the upper left.
yeah.
And another one in the lower right. I'm sorry, lower left. There's another galaxy. That guy, yeah. Whew.
Okay. It's
What
back
does the 15 in front of the designation, that number mean?
15 is this is the 15th slide in the presentation.
Oh, okay.
I put an extra number out front and the software lines it up.
Okay.
Puts them in order. Some software does. This one doesn't. This one can disregard it. So oh, no, it's doing okay. Now, as long as we're looking at that comet, right near it is the Mira, the wonderful star, and it travels. It has quite a range of brightness, and this shows it when it's in 2004 when it was bright, and this shows it right there in 2005, 30 October, a little over a year later, and it's gone. It's simply not there. So it's quite a large, it's a variable star. It's been known for a long time that it was a variable star. You can pick this out with your naked eye. You can see it.
Yeah, that's why they called it wonderful, you know, a wonder, you know.
Yeah,
It
wonderful.
was there and then it wasn't.
Wonderful. What not
Well,
wonderful.
wonder, yeah.
Wonderful.
I mean, in
This-
Spanish, mira means look, but this thing's taken from Latin.
Now, this is a picture of Myra
Wow.
taken here we are. It's a red giant variable star in the constellation of Cetus. This is an ultraviolet wavelength image. It's a mosaic from the Galax satellite, tail stretching 13 light years across space behind it.
Wow.
The tail consists of hydrogen gas blown off the star with the material at the farthest end of the tail having been emitted about 30,000 years ago. The tail-like configuration of the emitted material appears as a result from Myra's uncommonly high speed through the interstellar medium relative to the Milky Way's gas. Myra itself is seen to be a small white dot in here.
Is
There.
this the one they call the Wanderer?
No.
No,
Okay.
you're confusing your W's.
Okay.
Now this could be primarily it's hydrogen. Myra could be a large star that is throwing off its outer layers. It could be a Wolf-Rayet star. I'm not familiar enough with it.
It got a white dwarf companion.
Oh, does it? Okay. It's the ticking time bomb. Let's put it that way.
Yeah.
Seems to be something rare to me. I don't remember too many stars that have tails like comets.
A lot of them do.
Really?
Yeah.
Just we're not tuned to the wavelength to see it.
Yeah.
And
Ron, it represents, I would say, Ron, it represents a classification of stars. You know, Myra type variable stars. They have really long periods, 300 days, ish, something like that.
And it's an oscillation. It's not a
Mhm.
star.
Well, wouldn't they have a common name for them, like the Wolf-Rayet you
Yeah,
gave?
they call them Myra type stars.
Myra type variable stars, yeah.
Oh, this was just a couple of days ago.
I added this over the weekend.
What is this?
No
The
sunspots.
museum had their open house for everybody, and the club were visited by 500 people going out to see the sunspots and prominences. This is what they saw.
Yeah.
Nothing, nada, no sunspots. It's
Well, Jerry, they're back.
2
They're
days.
back. They're
What's
back.
that?
I was going to say they are back now. The
Yeah,
sunspots.
we had now we had a few sunspots and no prominences.
Yeah, but when it was clear like this, at least there were prominences, so the H alpha view was good.
That's right.
Yeah, a little bit. We had a few little ones.
Yeah, this is a visible light picture.
I mean, back when it was empty here.
Oh,
yeah.
yeah, we had great prominences.
So does the 11-year cycle, which turns out to be 22, does that mean we're at a low point
No.
or at a high point?
We're at a high point, but it's starting to trend down.
Yeah.
Huh.
Look at that.
Now this is a single star group that's photographed as it changed as the sun rotated. So this is several weeks across here.
Mhm.
And this was taken in August of 2024, so about 2 years ago. And these are very beautiful sunspots,
Yeah.
but it shows what you can get sometimes. Now, you'll never see this in one picture if you want to look at the star. This is a multiple exposure.
That's amazing. And Ron, in this region that he's showing us, it takes the sun about a month or so to go around once.
Yeah.
That was going to be my question.
Yeah,
You know,
this is several weeks.
I
That's
read the other
thinking
day
about-
that the 11-year, 22 years, and somebody was talking about an 88-year cycle.
I hadn't
80
heard that one, but
sounds like multiples of the 11 or the 22 is what it does.
I'll bring it in, Chuck, and show you the.
Maybe it's from somebody, Tim, who plays the piano.
Yeah, yeah.
This was a really hard picture to steal off the internet because it's interactive. And every time I'd touch it to copy it, it would jump to a setting that I somehow activated. But this shows sunspot cycles from 1985 minimum here. These are the 11 years, so 96, and that's about 96. See, that's about 11 years, and then 11 years and 11 years. This is what we're in now. This is up to the end of 25, and here we are in February 26. And This is a solar minimum and this is solar maximum. This is cycle number 25, this one here that we're in. And these are probabilistic estimates of what we're going to see. And you can't see it here, but it's shaded so that they have different probabilities. There's different shadings, and those shadings are down here. You have to really be able to get it high resolution, which I can't do on this screen.
But over it's more over to the left is where it says that's the 50th percentile probability.
And
Oops.
Ron, you can see it's in a downward, the peaks are coming down, down, down until now, Do you see them going down, 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 the peaks?
Sure, but what we're looking
And
at
then-
is on a cosmic scale, the sun is pulsing, right? Slowly? Or
No,
bulging or going back or
Yeah,
no?
that would be hard to pull off, another cycle within a cycle.
Well,
It's an interesting observation, Ron.
no, the sun isn't pulsating that much at all, Ron.
No.
This is just magnetic activity.
And science doesn't know why it does it on 11-year scale?
Well, it's a combination of the rotation rate and the magnetic fields.
Yeah.
Something changes, it either heats up a little or cools down a little?
No. It's magnetic fields.
Yeah, not in total.
Really?
So we will have it. If you look at this in a couple of weeks, there will be a point up here that goes all the way down to there for one day.
Yeah.
When are the aurora really kicking up? At a high point or a low point?
High point.
High point?
Yeah.
Yeah,
And in
these
March
points
and
represent-
October are prime months for auroras because that's when the magnetic field of the Earth and the magnetic field of the sun kind of align and give you a channel for these ions to come and hit the upper atmosphere.
And Chuck was pointing that out to the public yesterday. It was pretty neat.
But I'm thinking the prominences and the flares also peak with those peaks,
Yes, that's magnetic activity on the sun.
and the low points we don't have many flares and prominences.
You can still have them, but you don't have as many. Yeah.
Yeah, got it. Interesting. And they probably think most stars do this. We just don't have a way of measuring it from a distance.
No, we measure it.
Do we?
Yeah.
Well, to me, it almost seems like a form of variable stars. We used to feature variable stars or Cepheid variables. That means something's changing.
Yeah, they're pulsating. We aren't.
We can, Baron, Ron, we can see planets moving across stars way far away from the Earth. It's how we spot exoplanets. Those planets block the amount of starlight from those stars that's roughly equivalent to massive collections of sunspots. So we can detect sunspots on some stars if they're close enough. We can't
They
see
can
the
actually
spot.
sort of image them on some of the larger stars.
Yeah.
Well, what about
We're
the
not the only star that has this. We also have a lot of flare activity on other stars that we can detect. And the hope of Proxima Centauri is a fool's bet, because that type of star is a small red dwarf. And while there's a planet in its temperature sweet spot, Goldilocks zone, that star erupts and basically sterilizes any planets out there. And the one that's in the Goldilocks zone is believed to have absolutely zero atmosphere.
Not much of a Goldilocks.
Oh, no, the Goldilocks just comes down to a certain distance that if other conditions were right, water could be a liquid there.
Can I ask here, Tom, you mentioned that the peaks are going down there.
I just noticed that, and then Ron was reading another subcycle into this, which is probably not the case.
And there's a longer term cycle down below in that squiggly line, and you can see there's like 100-year.
Yeah.
Okay.
Yeah. It's
That
like,
might be the 88 that somebody was talking about.
right. That'd be about right. Things beating, Tim. That pattern is beating.
Yeah.
Like you have two instruments playing off, key a little bit,
Yeah,
Basically,
the thing that's common when I play my guitar is beating between two. It should be the same.
Does the sun have a basic polarization like the Earth? There's a north and a south to
It
the.
flips. That's
Yeah.
what's happening in this 22-year cycle.
Yeah.
Okay, well, our North Pole now, did we use the word positive? It is magnetism, right? It's
You don't use positive and negative with magnetism.
North and south.
just
North and
north and,
south. Yeah,
and do
and
we,
that migrates, Ron.
and we do have it on the sun.
Yes, but it flips. Every 11 years it flips. So it's a
Flips?
22-year cycle for it to come back.
Oh, you mean the north goes to the south
Yes.
and vice versa?
Yes.
Yeah.
Is that what they're thinking is going to happen to the Earth?
Yes.
Well,
It's
it's a
many
different,
times in the past.
yeah.
Does that disrupt things? Is that pretty bad other than our
Just like the sun, the Earth doesn't have one magnetic field. The magnetic field that we view is the vector sum of all the different dynamos inside the Earth. And they have a preponderance one way or the other. And when they flip, it's not like throwing a light switch. They flip by changing a little bit. There are places where you would expect your compass to point south, point north, and it actually points south. So there's a few areas on the Earth where we're experiencing at least a degradation of our magnetic field.
Yeah.
And the main effect it has is that it can let more cosmic rays come in because during some part of that flip, you can get lesser magnetic field protecting you from cosmic particles coming in.
Yes, and that triggers evolution, which has fun when you break all the DNA chains.
And Ronnie, if I have this right, when I first heard this flip, I thought it was like instantaneous, and they said no, it's like it when it goes to the minimum, like the north and south come together, and then they change.
Yeah,
and they go the other direction. So it'd be like coming like this and then going like that.
It happens for the Earth about every 100,000 years. So we've been through it a lot.
Mm-hmm.
And with this cycle on the sun, if you see a picture like that picture we had earlier, the sun with the multiple images of the spots going across, if you do that for a whole cycle, you get what's called a butterfly diagram, because they start in the extremes of the hemispheres, the north and south. And then as the cycle progresses, the spots move closer and closer to the equator of the sun. And then that's when things flip. Then it starts going the other way.
But why is this different from the way we measure magnets, for example, positive and negative, or the protons?
You don't measure magnets by positive and negative. Magnets are north and south.
I hear the word positive and negative. We apply them to protons and electrons. Isn't that the same
That's an
thing?
electric charge. That's not magnetic.
Those are charged particles.
But
I have trouble with it too, Ronnie.
Electrical gives us the magnetism around a coil, or
magnetism is produced by moving charges, moving electric charges. There is no magnetic monopole. You can take an electron and that's either positive or negative. Actually, electron is negative and a proton is positive. There is no equivalent magnetic monopole. There is no particle that's just north. North and south always occur together. The magnetic field lines never end. They are produced by moving electric charges.
You know, when I had to deal with this, Ronnie, is when I was doing the solar stuff on Sundays. I would explain to people that sometimes the sunspots travel in pairs, and one will be North Pole and the other one will be South Pole. And I used to say positive and negative, and Chuck and Jerry kept correcting
You're the one. You did.
You're the one that started that. Uh-oh.
Yeah, and I was the one that got corrected by Chuck and Jerry for about a week or two until it got through all the sawdust.
Well, maybe that's what we're looking at. That looks like one of those sunspots is in the northern hemisphere and the other in the south.
Yes.
Yeah. Ron, I was just going to mention a really interesting thing about, our magnetic north is, and I mentioned it migrates. Well, it turns out when Lewis and Clark were going across the country in the early 1800s, they would do some sightings on the pole position, which is kind of up in the Hudson Bay area. And you could see from their measurements a couple of 100 years ago and current measurements that pole has migrated. It has moved.
Yeah.
Very active ball we're living on. very active.
We got a question by a fellow yesterday, Tom. I had to turn it over to Chuck because I didn't get it. It was something about that.
Oh, yeah. Yeah, it's
Yeah,
fascinating. Lewis and Clark actually took sightings, and you can see they're different now. Yeah.
And Ronnie, when we're talking about a north and a south pole magnetic field in a sunspot pair, we're not talking about one is above the equator and one is below the equator. You know, one is north of the equator, one south of the equator. Individual star spots like you see here can have both north and south polarity.
Yeah.
And one is leading and one is trailing, and that's the opposite in the other hemisphere. So so there aren't really any obviously paired sunspots here, but you know, maybe the big one with the little one trailing it, one of those is north and the other one is south.
Oh, and you guys can help me with this. Whenever I bring this up, the north and south of the sunspots, is the are the, is the plasma that pops through the weak spot, does it travel from north to south or south to north? Would it go from I don't know.
I understand your question. It's a good question.
Yeah.
I'd have to write the Lorentz force equation and decide on that. It doesn't pop right into my mind how to do it.
I mean,
But
the
there is a
convention
direction that they go.
Yeah, the convention, of course, is out of north into south, right? For a magnet, a bar magnet, out of
Okay.
north into south. That's how
Out
we
of
draw the
north to
lines.
south. Okay, I'll
Yeah.
remember that. Thank you, Tom.
Yeah,
But that might not necessarily be how the plasma travels because
that's right. That's right. Yeah.
Oh,
The
okay.
plasma is going to circulate about the lines, right?
yeah.
Yes.
Like
Well,
And,
you know,
and the
then
question is, was it clockwise or counterclockwise? And yeah.
if you're an electron, it's going to be opposite of a proton.
Okay.
You can always tell students that are learning electromagnetism because they're at the dinner table going things like
Oh, the three things.
and things like this, and everybody asks, "What are you doing?"
Right.
Yeah, yeah. The guy did that. Michael did that to me yesterday.
Yeah.
Well, I'm trying to
Okay.
understand everything you guys have just said. And maybe it has to do with my stupid question about where the lines of force go in are not exactly where the North Pole, the top end of the axis around which the Earth and the Sun both spin. Why wouldn't that be the
You're
same?
thinking of a single simple bar magnet. The sun is not a bar magnet.
Right.
The sun, if you want to picture the magnetic fields in the sun, go get about 100 rubber bands and squeeze them in your two hands to make a ball out of them. And then rub this ball together. And the individual rubber bands will represent the magnetic field lines in the sun. And that's a good representation out of it. Some of them will wind up and try to stick out, and you'll have to be pushing them back into the ball with your fingers. Those are sunspots.
Yes.
Okay, so the
And
whole
Ron, that's
ball.
the famous rubber ball theory.
Yeah.
But Ronnie, your question is exactly what the visitor yesterday asked about the Earth's magnetic field. It's exactly that.
Okay.
I just wonder if where it goes in, what is the magnetic? Is that what it's called, the magnetic North Pole? And it's not where the Earth spins axis.
No,
Right.
no,
They're not aligned with each other.
They're not
Right.
aligned. Yeah.
Does that stay where it is, and the Earth just keeps kind of turning in it, or does it go with the Earth and that
It
center?
goes a little bit with the Earth because the North Pole does not correspond with our rotational North Pole. That's because all these the naming of things came within the last magnetic field shift. If we go through one, which we're apparently about starting, if we shift again, pretty soon the south magnetic pole will be at the North Pole.
Yeah. And Chuck, you can correct me on this, but I understand that the original pier at the Palmer was poured magnetic north. Is that what? Oh my God. I think the declination here is like 13 degrees.
12 or 13, I believe you're right.
Yeah. And Ronnie, picture, you know how we have pulsars. You have these rotating neutron stars, and the reason we have a pulsar is because their magnetic field poles are not aligned with their rotational axis. Right. And it's out of those north and south magnetic field poles that the jet comes that sweeps by us. And so as the thing rotates around its rotational axis, it's swinging these magnetic fields around and sending beam past us like a lighthouse.
Right.
Oh, wow.
Yeah, so it's called the lighthouse effect.
Huh.
So pretty much all bodies in space then do that, don't they? All planets, all stars have a center, they're all spinning, right?
Yeah.
They do it worse than we do. We are relatively stable over long period of times because we have such an outsized moon,
Yeah.
which helps us be stable.
Huh.
Yeah, and Ronnie, there's a moon around Saturn, Hyperion, that is the center of mass is not the center of the body, and so it has totally chaotic rotation.
Yeah.
Wow.
Wow. Now for
We had
Milan.
one of the comets
Yeah.
we looked at, or no, one of the asteroids we looked at too, had chaotic rotation. I forget which one it was, but I got a headache trying to think about it.
Everything's tumbling.
Very interesting, Jerry. This stuff's interesting.
Yeah. Speaking of rotation, Ron, there was a really nice article recently in the New York Times about how comets rotate. And they spin one way, slow down, and start spinning the other way. It's pretty neat. Yeah.
They don't,
Everybody spins. It'd be unusual not to spin, I think.
they
Yeah,
wouldn't,
and
they wouldn't spin like a rifle bullet in the direction they're going.
no,
No, no.
When I worked at Hughes Missile Systems Group, we were working on a infrared guided bullet. It was called CLIGUP, Cannon Launched Infrared Guided Projectile. And so we wanted to understand how tank shells and howitzer shells related to the direction they were going. And it's not as you think, obviously. I mean, it's not real simple. When it's rifled and the bullet is spinning, then when it's going up in its trajectory, it's pointed, it's like it's skiving with its bow too high up.
yeah,
And then when it passes the peak and it's going down, it skims with its point too far down. So it's not a simple motion like you think.
How in the world would they know that?
And there's a really interesting rotational effect where a certain shaped object will spontaneously stop and rotate and flip its ends and continue rotating. They discovered it on the space shuttle or on the space station. I forget the name of it, but I'm going to include it along with the Milankovitch cycle at the beginning of our next talk.
there are some toys you can get that are these
Yes.
offset masses that you can set on a table and start spinning, and they'll spin for a while, and then all of a sudden they'll flip and start going the other way.
Oh, wow. Interesting.
So this whole discussion we've been having for the past few minutes is the Milankovitch cycle?
No, no.
No, we never started the Milankovitch cycle.
Oh, so we're going to postpone that a week.
Yeah, I used to teach this in geology, Jerry. I mean, this guy was way ahead of his time discovering this. Milankovitch, because I think it was in the 20s, right? Milankovitch?
I think it was suspected. I don't recall.
Hmm.
Well, I just know the effect. I don't know when. I'll get its history and add it.
That's going to be fun covering this guy.
Yeah.
Well,
This is what a lot of people that try to claim there's no climate change. They say, well, the Milankovitch cycle completely refutes climate change. And it doesn't.
No.
Yeah, they just don't look at the rate of change. They ignore that.
So we'll cover that too.
That'll be neat. Yeah.
next
Really
week.
fascinating hour, Jerry.
It's a good one.
that was my thinking on why Trump wanted Greenland, future beach property. Well, gentlemen, I think we did it again. I just had one last question, and that's something that I'll learn from our guest speaker Friday night. But just going in, what are the moons that spew ice volcanoes, the ones around Jupiter and Saturn?
Europa on Jupiter, and
And-
Enceladus on Saturn.
Enceladus is Saturn. So those two are the main ones spewing the not so hot stuff. I assume that
Yeah. Ice.
because her title is called Where the Hot Stuff Is. And if she's going to cover ice
Well,
volcanoes,
hot is a relative term.
Yeah,
oh, I understand that. I know that. Okay.
and it's Triton around Neptune also.
Yeah.
Okay, it's going to be an interesting evening, and we get the big auditorium. And gentlemen, we've started our 6th year together, no end in sight. We're all going to slowly conk out and die on this channel over the years. So thank you for kicking it off, and we'll see you at the party next Friday, and following Saturday of the following weekend we'll be outside, and we have our own special way of saying Farewell, everybody. It goes like
Live
this.
long and prosper.
Asta Nebula.
Hasta